Welcome. Today we're going to be looking at Newton's laws of motion at your fingertips. Easy and simple. So, there are three laws of motion as postulated by Isaac Newton. And the first law is quite simple. And this law says that every object continues in a state of rest or uniform motion in a straight line until that object is acted upon by an external force. This Newton's first law is also called the law of inertia. The law of inertia. Alright, so what's the connection between this law and the law of inertia? Alright, so to start with, what do you understand by inertia? Inertia, rather, you can pronounce it inertia, you can pronounce it inertia. Alright, so inertia is the reluctance of a body to change its state of rest or uniform motion in a straight line. I can take it again. Inertia is the reluctance of a body to change its state of rest or uniform motion in a straight line. All right, that's what inertia is. Now, if you notice something, if an object is moving, all right. So take for instance, a bicycle is moving, all right. You discover that that bicycle has a lesser reluctance compared to a motor car, a vehicle moving. All right. Why? Because the bicycle has a lesser mass compared to the car or a lorry or an heavy-duty vehicle. Why is there difference? Why are there differences in this reluctance? The reason why there are differences in the reluctance is because if you look at these two objects in motion, you will discover that these two objects are of different masses. So we can say that inertia is a function of mass of the body. Inertia is a function of mass of the body. All right. So yes. So inertia again is a reluctance of a body to change its state of rest or uniform motion. And this reluctance is a function of mass. So what's mass? Simple. At your fingertips. Mass is simply the quantity of matter present in a body. All right. That measure, that quantity of matter present in the body, it's measured. It's of course it's measured in kilograms. That's the SI unit of mass. All right. So you may be facing times like this in the first law. What's initial mass? Initial mass. Initial mass. So I've told you what inertia is, and I've told you what mass is. So what's initial mass? All right. When we're talking about initial mass represents a resistance to any type of force. A resistance to any type of force. All right. That is what we mean by initial mass. All right. Resistance, reluctance to any type of force. Remember that this force we are talking about is a function of mass and acceleration. All right. If it is an horizontal force, mass times acceleration. If it is a vertical force, it is mass times acceleration due to gravity. So these are just points you can note about the Newton's first law of motion, which is very easy to memorize. Newton's second law of motion. In the Newton's second law of motion, which is simple to state, it states that the rate of change of momentum is proportional to the impressed force and takes place in the direction of that force. The rate of change of momentum is proportional to the impressed force and it takes place in the direction of that force. Now, Newton's second law of motion Newton's second law leads to the formula F is equal to ma. All right. So when I'm talking about this F is equal to ma. All right. I'm referring to force. This is what the second law leads us to. Now, how does the second law lead us to this? This is what we're going to look at right now. We continue. You can see that from the second law, rate of change of momentum is directly proportional to the impressed force. Conversely, this means that force, that's the impressed force, is directly proportional to the rate of change of momentum. And it's important to note that rate of change of momentum, whenever you hear rate, that means that change in momentum is a function of time. All right. Rate of change of momentum is given as change in momentum all over time. Remember, momentum is a product of mass and velocity. That means that change in momentum is simply given as initial momentum, or rather final momentum minus initial momentum. Final momentum minus initial momentum. Final momentum minus initial momentum. All right, that is the formula for change in momentum. So the final momentum will be given as mass times the final velocity minus the initial momentum is given as mass times the initial velocity. U is the initial velocity, all divided by time, all divided by time. We continue. You see, factorizing this gives you m into v minus u all over t. M into v minus u all over t. If you look at this very well, from your equations of motion, the first equations of motion that says that v is equals to u plus at. If you make acceleration the simple formula, you're going to see that v minus u is equals to at. Divide both sides by t, you can see that a can also be given as v minus u all over t. Why did I show you that? I showed you that so I can point out to you that what we are seeing here is similar, is synonymous to the value for acceleration. So you can see here that everything here, all right, can be given as f directly proportional to ma. Remember, in mathematics, we can remove this proportionality sign, we can replace it with an equality sign. Replacing that with an equality sign, you will see that f is equals to kma. The constant came in because we replaced the proportionality sign with the equality sign. And experimentally, the value of k is given as 1. That means that the formula for force becomes ma. It has been proven by Newton's second law that impressed force is directly proportional to the rate of change of momentum, which leads to the force given as mass times acceleration. We continue. So from this point in the derivation that follows the mathematical expression of Newton's second law, you remember this step? All right. So from here, we can quickly still say that this is equals to k m into v minus u all over t. Remember, experimentally the value of k is 1. So this is still the same thing as m into v minus u all over t. We're going to discover something as we pass through this route. In this route, you will discover that if you cross multiply, ft equals to m into v minus u. M into v minus u. Now, this, the product of force times time, is called impulse. Is called impulse. Whereas, do you still remember this? This is called change in momentum. So, what is impulse? Impulse is the product of force and time. So when force acts on an object over a period of time, what that object experiences is an impulse. You can also use the word impact to explain this. The impact an object feels, all right, at collision, you can say, all right, is the product of force times time. Now, the unit of force, of course, we know that it is Newton and the unit of time is seconds. So impulse is given the unit Newton seconds. You can also see here that this unit, Newton seconds, is this physical quantity is also equivalent to change of momentum. So even though the unit of mass is kg and the unit of velocity here is meters per second, all right, you can see jam questions that will come up. Which of the following quantities has the same unit or dimension as impulse? All right. So even though the unit of change of momentum is kg meters per second, all right, we can conversely say that it is equivalent to Newton's second. Is equivalent to Newton's second. So impulse has the same unit and dimension as change in momentum. You may be doubting how. I can prove this to you because force times time. Force is given as mass times acceleration times time. Mass is kg, the unit of mass is kg, the unit of acceleration is meters per second square, and the unit of time is t. So this is the same thing as kg, meters per second square, this is seconds. Meters per second square times second is like saying m all over s times s squared times s. So you can see that this s cancels s squared. Do you know what that becomes? That becomes kg meters, is just 1 second remaining here, meters per second. So you can see that kg meters per second from force is the same as kg meters per second from change of momentum. So we can also say that impulse having the unit, that's the SI unit as Newton second, we can also say that change in momentum has the SI unit is Newton second. So I have successfully proven to you that these two quantities, impulse and change in momentum, have the same SI unit, all right, and they also have the same dimensions, all right. So Newton second. So by this, so you can pause this video and look at it again, so you can understand that this is the same as this, which is Newton second, which is mass times acceleration, which gives you this, is the same thing. It's the same thing. Are you saying this? Are you saying this? So it's the same thing. It's important that you note that. We continue. Newton's third law. The third law says that to every action there is an equal and opposite reaction. To every action there is an equal and opposite reaction. You can also state it this way, that action and reaction are equal and opposite. Very simple, at your fingertip. You can state that. All right. So what's the application of that? If you look at someone trying to shoot a gun, all right, you would see that as the bullet from that gun moves forward, that gun seems to jerk backward. The backward jerk of that gun is as a result of what we call recoil. There is a recoil velocity. The recoil velocity goes in a direction which is opposite to the direction of the motion of the bullet. So as the bullet moves forward, the recoil velocity is the velocity acting in an opposite direction. As the bullet moves forward, the gun jerks backward. Bullet moves forward, the gun jerks backward. Bullet moves forward. So this backward jerk is as a result of the recoil velocity. So you can see how simple it is to memorize Newton's laws of motion. The first law, the second law, and the third law. All right. Watch my next videos for more lessons on this. Alright, so you can like, you can subscribe, and you can hit the notification bell so that you will be notified whenever I release new videos. Don't forget, learn with Master. Alright, so you can share this on all your social media handles, and see you in my next class.